Hello and welcome back to the Science of Concrete Materials class. This is lecture number 25 of the class, and we will continue our discussion on the aggregates module. Last lecture we finished the discussion on the aggregates properties required for mixed design, and today we will discuss the durability of aggregates. So since aggregates make up the bulk of the concrete, any lack of durability of the aggregate will have disastrous consequences for the concrete. Fortunately, in most parts of North America, there are few problems concerning durability of aggregates. In other areas, however, special screening tests may be required routinely to avoid problem aggregates, or special measures must be taken to counteract the effects of undesirable aggregates. So the second approach is especially important where deposits of high quality aggregates have been worked out and more marginal material has been brought into use, again because of the scarcity of good aggregates. So the lack of aggregate durability can be conveniently divided into physical and chemical causes. The first one is concerned with susceptibility of aggregates to freezing and thawing, or wetting and drying, as well as physical wear. The chemical durability problems are concerned with various forms of the cement aggregates reactions. Of the various procedures used to measure aggregate durability, basically field performance is the best. Okay, the next best choice involves tests that evaluate the aggregates when cast in concrete. But these tests are usually more time consuming than tests performed directly on the aggregates. And therefore, a number of durability tests have been developed that can be run directly on the aggregate itself, just for convenience and for the sake of time. A thorough petrographic examination can tell a lot about potential durability of an aggregate and may eliminate the need for embarking on a lengthy tests program. So that is something to keep in mind. I know it's a specialty subject, specialty skill, but it goes a long way in identifying potential problems with aggregate. It is important, in aggregate evaluation that proper sampling practices to be followed as laid down in ASTM C702 and D75. Okay, so we're talking about whatever testing program you're going to adopt. Most importantly, representative samples of whatever aggregates you're testing in order to make sure the tests are representative of your material source. So let's look at the durability issues we're talking about here. Let's look, at the physical durability. Okay, soundness. The rocks that undergo volume changes due to wetting and drying are rare. But, aggregate is susceptible to volume change during freezing and thawing cycles. Freezing can cause internal stresses to build up as water inside the aggregate freezes and expands. Basically, a critical size can be calculated below which freeze-thaw is not a problem. However, for most rock, it is greater than normal sizes, all right? Okay, we're still on the physical durability, the wear resistance. A good aggregate will be hard, dense, strong, and free of porous material. The abrasion resistance of aggregate can be tested by the Los Angeles abrasion test, ASTM C131 and C535, which involves the ball milling of the aggregate with steel balls for a given time, then sieving the material over number 12 sieve and measuring the mass loss. The test does not really correlate well with concrete wear in the field, but rather appears to be a better measure of the tendency of aggregates to break during handling. The chemical resistance. We have a familiar term here. I mentioned it several times before, the alkali aggregate reaction. Basically, it is an expansive reaction between some reactive forms of silica in the aggregate and the alkalis in the cement paste. The result is overall cracking in the structure, manifesting itself in map or pattern cracking at the surface. This reaction can be controlled most easily by using low alkali cement. But if you remember about the manufacturing of cement and using waste product, due to changes in the manufacturing, low alkali cements may not be feasible always. So a better approach is to avoid aggregate with the potential or proven record of reactivity. Also, a low water cement ratio will slow down the reaction but will not stop it. Also to remember, no adverse reaction will occur without external water. So this is mostly a problem in exposed structures. Okay, another form of the alkali reaction is the alkali, aggregate reaction. Some sand gravels, found in river systems of Kansas and Nebraska are highly reactive and cause map cracking. To solve it, replacement of 30% of the aggregate, with crushed limestone is effective in reducing the damage. Basically, it results in the separation of flat clay minerals, causing, very slow expansion. So this is one way to partially mitigate it or alleviate the problem. Another form is the alkali carbonate reaction, which is basically an expansive reaction involving clayey carbonate rock. The reaction in this case can be controlled by using low alkali cement. Again, we said the low alkali cements may not always be a luxury that is available, or blending aggregate with other less reactive material. And again, we're trying here to deal with the scarcity of aggregates. I mean, if you have the choice, you will not use aggregates with potential carbonate reaction or alkali aggregate reactions. So, but sometimes you have no choice. So ASTM has set standards for deleterious substances in aggregates, which depend on application. So this can be divided into two categories of impurities. First, solid materials, which particles pass in a 200 mesh sieve. These fine particles may increase water requirement and again also interfere with the surface bonding between cement and coarse aggregates. We have these soluble substances which, when organic matter react chemically with the alkaline cement paste, forming soluble organic compounds which will affect certain time. So aggregates, obtained from sea or dredged from the sea should be thoroughly cleaned to avoid problem from salt contamination, which also another soluble substance that may cause problems. A second category is the unsound particles, which are soft particles such as clay, lumps, wood, coal will cause pitting and scaling at the surface. Organic compounds can be released, which interfere with the setting and hardening. The weak material of low density, which have low wear resistance, should be avoided. And again, any aggregates, and again, we're talking about testing of aggregates, either where aggregates have been known to cause problems. Also, if not, certain tests sometimes are required to make sure you eliminate any of these potential issues. So the evaluation of aggregates, and again, I'm repeating, it should be noted that tests on aggregates alone are not an effective means of predicting aggregate performance in the field. Tests for aggregate properties for mixed design are straightforward, the one we talked about last lecture, and I will have another lecture about the calculations. But tests on durability and performance really have limitations, which we talked about, the physical tests and the chemical tests. So some of the physical tests, the abrasion test, abrasion resistance, we have the abrasion resistance test, which basically the Los Angeles test for abrasion, which involves the ball milling, as I said, in an aggregate sample for a given time, measuring how the sample particles are reduced in size. We have the scratch hardness test. This assumes a relationship between the hardness and abrasion. Neither of these tests is an accurate or reliable measure of the concrete hardness. So an indication would be to test the concrete itself, because the test on the aggregate may not be indicative of how it will perform in the concrete. We have also the frost resistance, the soundness test. This basically is a simulation of ice formation in an aggregate sample. The sample is saturated with a solution of sodium or magnesium salt and dried in an oven. The salt crystals, which form in the pores, simulate ice. Correlation between this test and field tests are not good. Again, a better approach is testing aggregate and concrete. The chemical tests, we talk here about the alkali-silica reaction. There's a rapid and reliable test for alkali aggregate reactivity. Has not yet been developed. Okay, so most acceptable tests require long curing times of about 6 months. In this test, the aggregate is ground to a fine sand and used to make a variety of mortar bars. The mortar bars are stored in hot, moist conditions, to accelerate the reaction. Expansion of the sample is measured and compared to ASTM specifications. Again, it's not the best, but that's the available tests. Okay, so we talked about testing of aggregates, and I said also, speaking of the subjects of the availability of aggregates, and we sometimes are faced with a problem in some locales where good sound aggregates that meet ASTM tests and requirements are not readily available. So sometimes we have to improvise to deal with whatever situation we are dealing with. So if an aggregate does not pass the ASTM test, an engineer may choose to try to upgrade the material. The beneficiation may be useful in areas, and as I said, where the aggregate is scarce. So there are several possible ways of treatment. First, crushing. Soft porous rock may be removed by crushing. The heavy media separation, where lightweight particles may be separated by floating them to the top of a liquid. Reverse water flow or airflow, used to remove lightweight particles like wood. We have the hydraulic jigging, which is basically stratification of aggregate in a vertical pulsation of water. In this case, lightweight particles separate to the top. We have the elastic fractionation. Again, the aggregate in this case is dropped on an inclined steel plate. The hard particles bounce, higher off the plate than do softer particles. Appropriate placement, of collection bins, can provide good separation in this case. Washing and scrubbing, removes fine surface particles. And I know if you just read these, you might be, rolling your eyes. It sounds like desperate ways for the sake of bringing good aggregates to use, which basically they are. And again, when you are dealing with the scarcity of good source aggregates, you cannot just stop making concrete. You have to improvise, and you have to be creative in ways to find economical ways to provide aggregates for the making of concrete. That is good compliant aggregates I'm talking. Okay, so also we can use waste materials as aggregates. So basically the use of waste materials as aggregate in concrete is gaining increased attention, especially in view of our, escalating solid waste problems. A wide variety of materials are being considered as aggregates, garbage, building rubble, industrial waste products, and the mine tailings. All of these potential aggregates, should be evaluated on their economy, compatibility with other materials, and concrete properties. So successful utilization of waste material as aggregate depends on anticipating potential problems and ensuring that the properties of the concrete will remain unchanged. And again, guys, what I mentioned here, the making of concrete becomes sometimes an art. You have to be creative. You have to think outside the box. You cannot, of course, make concrete without considering cost. Finding good aggregates sometimes, if it's not available in your locale, or even if it's available in your locale at a high cost, you might have to, as I said, think outside the box, be creative, and find ways to make concrete more sustainable by reducing the cost. And at the same time, we're talking about helping the environment. And by using waste material, if you can turn these into compliant aggregates that will be used to make good concrete, you are a double winner in this case. And there is a lot of room for improvement for whoever wants to explore this subject. Okay, so there are some special aggregates referred to as special aggregates, as it was mentioned before, that most classification of aggregates, was on the basis of bulk specific gravity, heavyweight, normal weight, lightweight aggregates. The variability in density can be used to produce concretes of widely different unit weights. But the different kinds of lightweight and heavyweight aggregates are described here, while the properties of the corresponding concretes will be discussed in some other class, will not be discussed in this class. We're talking about here just the special aggregates for reference only, not to get into the properties of the concrete made with these aggregates. So of the special aggregates, we have the lightweight aggregates. A general characteristic of the lightweight aggregate is high internal porosity. Most of these materials are synthetic. However, some natural materials can be treated to provide low specific gravity. Clays, shales, or slates, will bloat at high temperature, resulting in an expansion in volume. Other synthetic materials are produced using bioprocessing techniques such as volcanic glass, slags, or waste glass. The lightweight aggregates have high absorption capacity associated with their high porosity. But, some materials have a coating resulting from the fusion process, and water cannot penetrate them. So this coating can be damaged though during handling, resulting in abrupt increase in absorption. And again, these lightweight aggregates, these special aggregates are used in special applications, and of course they are not used in structural concrete that will have to be of a certain strength and durability characteristics. So these are not fit for that use, just as a reminder. We have also the heavyweight aggregates we mentioned before. This is a material with a high specific gravity. These types of materials are mostly used for, radiation shielding, an application where high mass to volume ratio is required. We also have abrasion and skid resistant aggregates. These hard, dense aggregates used in heavy industry applications, where high resistance to abrasion is required. The strength of the cement paste and the cement aggregate bond are more important than the aggregate hardness. Keep in mind. We have something referred to as marginal aggregates. Use of this type of aggregate will require more care and thought and design. So generally, also more cost. So in considering marginal aggregates, there are 4 areas of interest. Concrete properties, the weakness of aggregate, the beneficiation, and the use of protective measures. And again, these are not common in use, but it does not hurt to know about them. Okay. So we come to the end of the of lecture 25, and next time, as I said, I'm going to have a lecture on the calculations and the remainder of the equations we use in the mixed design calculations. So until then, thank you and see you next time.